Physics Part 170. Thus, doubling the amplitude of a wave increased the intensity of the wave by a factor of 4. The intensity also depends on frequency. Intensity is proportional to the square of the frequency. For a wave of amplitude A and the frequency f of the intensity I is proportional to a square into f square. If the waves from a point source spread out equally in all directions, we have what is called a spherical wave. As the wave travels further from the source, the energy it carries passes through an increasingly large area. Since the surface area of a sphere is 2 pi r square, 4 pi r square, the intensity is W divided by 4 pi r square. Where W is the power of the source, the intensity of the wave thus decreases with the increasing distance from the source. The intensity I is proportional to I over r square, where r is the distance from the source. Wave equation. From the definition of a wavelength lambda, in one cycle of the source of the wave, energy moves the distance lambda. In f cycles, the wave moves distance f lambda. If f is the frequency of the wave, then f cycles are produced in unit time. Therefore, f lambda is the distance moved in unit time. Referring to chapter 3, speed v is the distance moved per unit time. Therefore, v is equal to f lambda, or speed is equal to frequency into wavelength. This is an important relationship between the speed of a wave and its frequency and wavelength. Examples. Number 1. A turning fork of frequency 170 Hz produces sound waves of wavelength 2.0 meter. Calculate the speed of sound. Using v is equal to f into lambda, we have v which is equal to 170 into 2.0, which is equal to 340 ms r raised to minus 1. The amplitude of a wave in a rope is 15 millimeter. If the amplitude were changed to 20 millimeter, keeping the frequency the same, by whatever factor would the power carried by the rope change? Intensity is proportional to the square of the amplitude. Here the amplitude has been increased by a factor of 20 over 15, so the power carried by the wave increases by a factor 20 into 15 square, 1.8. Now it's your turn. Number 1. Water waves of wavelength 0.080 meter have a frequency of 5.0 Hz. Calculate the speed of these water waves. Number 2. The speed of sound is 340 meter per second. Calculate the wavelength of the sound wave produced by a violin when a note of frequency 500 Hz is played. Number 3. The speed of light is 3.0 into 10 power raised to 8 meter per second. Calculate the frequency of red light of wavelength 6.5 into 10 power raised to minus 7 meter. A beam of red light has twice intensity of another beam of the same color. Calculate the ratio of the amplitude of the waves. Properties of wave motions. Although there are many different types of waves, light waves, sound waves, electrical waves, mechanical waves, etc., there are some basic properties which they all have in common. All waves can be reflected, refracted, diffracted, and can produce interference patterns. These properties may be demonstrated using a ripple tag similar to that shown in the figure. As a motor turns, the wooden bar vibrates, creating ripples on the surface of the water. The ripples are lit from above. This creates shadow in the viewing screen. The shadow shows the shape and the movement of the waves. Each shadow corresponds to a particular point on the wave and is referred to a wave front. The circular waves may be produced by replacing the vibrating bar with a small dipper or by allowing drops of water to fall into the ripple tag. A circular wave is illustrated in figure. This pattern is characteristic of the wave spreading out from a point source. We shall now see how the ripple tag may be used to demonstrate the wave properties of reflection, refraction, diffraction, and interference. We'll do the same in our next video.